All right. Let's hope it works. Yeah, I know. It's a spinning wheel for now. Nice.
Okay, please let us know. I'll talk about rectified one. This is a word which I had to learn myself, kind of know, but kind of don't. Rectification means cleaning up, setting things straight. We reverse to the resurrector, and you can imagine that this person is getting a lot of things straightened up. And so here is the Wikipedia or Oxford dictionary. In the electrical engineering, it's often used as a device. Rectification is the process of cleaning up AC current and producing DC. Okay, but generally, we say that we're just clearing up things. Okay.
Sasha, the slides are not coming.
I guess you have to stop projecting, right, and share it.
No, just through Zoom. There's a great.
On Zoom, okay. All right.
Well, you heard the introduction. Here is the word rectification, the definition of this. And so, like I said, people often talk about in the context of classical circuits in electronics. I will apply it to the quantum field. That's the goal. Why? I hardly need to argue for utility of this type of approach. We do have a time-dependent given systems. We do have now gorgeous experimental capabilities ranging from the large user facilities to some active control qubit platforms where we can actually actively drive materials or artificial materials. And the idea would be that maybe in the process of doing it, we can produce unusual quantum states which are either unavailable to us in equilibrium or hidden in some way. And so I will do a little bit of introduction about what I mean by induction of quantum order. An important player in this conversation will be inverse Faraday effect, which I will introduce. And then actually I will proceed with showing the examples of how we can use this idea of rectification to different quantum orders, different games we can play. Specifically, I mentioned something about so-called fifth or axial Faraday effect, which is a prediction. And then we can talk about the sort of games you can play with this in quantum rectification. So the central player in this whole conversation will be this triangle diagram. So you have a field A coming together with field B, and if algebra and causality or whatever, your field theory permits or your theory permits it, something comes in the C. And the diagram can rotate in many different ways. Okay, so for instance, I can rotate the C and B coming in and emitting A. So for those of you who remember the earlier diagram for the standard quantum electrodynamics, this diagram is zero in the vacuum. But for the matter, in the presence of the matter, it does not have to be. Okay, the symmetry held in the certain quantum diagrams is canceling out in the field theory. They actually getting modified and acquire their own life and become very interesting abilities in quantum theory. Okay.
That once. Side once.
Like once. Down.
Click on
On the slide. Maybe my computer froze, no? Okay.
Yeah.
Something works, but this is just a manual. Okay, so I have a basically pleasure working with a lot of people.
Okay. Yes, it worked.
All right, I've been working with many people. I think actually some of the work I'm going to show is done in collaboration. Priya is the main driver. There is a conversation about this attacks.
second interesting set of quantum atoms or quantum materials that are this project. So, but I specifically would like to point out the collaboration with experimental group of Stefano Panetti, where I'll show you some hopefully soon be published experimental results on the drive of the quantum paraelectric or ferroelectric state with light. All right, I already alluded to this. Driven quantum matter is interesting. We do have quite a bit of the very interesting progress made in terms of getting the resolution of the K space to unprecedented degree. Vidya gave a very wonderful talk, interesting talk about the local probes, where we can get to the limits of the spatial resolution and find out all sorts of quantum orders in real space. And what we have is coalescence of the space and time resolved probes coming in, or like bringing up interesting states of quantum materials. Right, and so time is an important part of this conversation. Now, Balatsky and company, they wrote very interesting review paper, or essentially position paper. A lot of this lately review papers become lobby papers for the big funding agencies. So I presume this was in anticipation of some funding from DOE or agency like that. So there is a very interesting summary on the so-called quantum materials in this review, and they actually basically discuss the whole suite of the time frequencies, so to speak. Equilibrium probably can apply, starting from static to gigahertz, terahertz, and so on, and all the games you can play with the quantum materials. So it's wonderful. I will just down select to a few topics I want to highlight. And it's going to tap into the interplay between the lattice effects, lattice dynamics of magnons. If you want the nonlinear harmonic effects, which fit in magnons, and also the idea of how we can manipulate this metastable states with light. Okay, so let me just show you a few examples of what we mean by the actual unusual order, dynamic orders. Right, and I would say right away that there is at least two approaches one can do it. One can do it in a linear way and a nonlinear way, and I will basically explain what I mean by that. And going forward, I would like to focus on the nonlinear effects of inducing quantum order. So it's often shown that, for instance, what the paradigm of this induction of the quantum order would be. Say, you have this pendulum. And for those of you who know, you have a Capacity pendulum. There's a bicycle problem in the control theory, how you maintain the base of this pendulum so you can bring it up so that the pendulum stays up. Right, so there's basically the planes, some of the planes, advanced planes flying on the edge of stability, and that's what gives them agility. Same here, you turn on and put the pendulum in totally unstable configuration, but with active feedback. So technically, what you do, you create an environment for the pendulum is inanimate object, but the pendulum thinks or the gravity is pointing out, and that's actually the whole core of the physics of the Capacity pendulum. Basically, you fool the system thinking they're creating metastable state, but they're used to be now. And therefore, if there is a low-lying set of excitations in some profile of the free energy that was nominally higher, then you can stabilize it in a transient way. So this example of the stabilized quote-unquote state, which could be in there as long as you keep driving it, but technically it's not thermodynamic. And this per se, what Ashwin is saying, I should say, that the thing is very similar here, that we do have now the platforms which will allow us to have very interesting topological or quantum phases appearing in driven states. But technically they are not the ground states of any time. So examples of this induction of the unusual order, for instance, was shown before, I would say, 10 years already. How you can shine the light and you can fool the insulator and thinking it's metal by doing the cross gap excitations and switching on and off metallicity at very fast time scale. Obviously, there is a lot of literature on the magnetization control, controlling magnetic degrees of freedom with light. I will mention a little bit about superconductivity with light, and that is a topic of great debate and discussion. But whatever the debate settles on, whether it's a full superconducting state or not, and this Cavalieri experiment is, Nevertheless, I think it's a very fascinating topic to produce some phase coherent state, the transient and equilibrium state. And what I will show you is suggestions and some experiments on how we can control ferrolipticity. Right, so, important player in this game is going to be Faraday effect. You know what Faraday effect is. You have a sample, you have a magnetic field along the beam of magnetization, and when you send the sample to linear polarized light rotates, polarization rotates with it. And the transmission is Faraday, reflection is scalar effect, but both of them show the magnetic activity of the sample. There is a reciprocal effect. So in this effect, nothing rotates, and then just send the linear polarized light, and it just rotates. The reciprocal effect is that if I send back in a non-magnetic sample, rotating polarization with light, which I can do by circular polarization before. I send a non-magnetic sample will acquire magnetization. Okay, so physics of this is fairly simple. I'll show you some example of this, like heuristics of how we arrive at it. By the way, this heuristics I wasn't able to find anywhere, so like we had to do our own spherical cow. That's kind of cartoon. You go to the great source of knowledge, go to Wikipedia, and it's basically inverse Faraday effect. It says about one part. That's it. Now, what it says is the following: you can basically in a point line AC field, the certain polarizations E and the star technically are not the same. So it's not E is not along X, it's not along Y, it's E plus Y. Add the monochromatic frequency, then you can get the DC magnetization produced as a result of that. And it's a for different languages, it's a Raman process, it's a 2-photon process, it's basically a process where you send 2 waves, and what comes out is essentially DC magnetization. Now, if you think about what the physics of this has to be, is that you're impinging the circular polarized light, so basically the photon comes in with some angular momentum. Some part of the angular momentum gets transferred on the medium. Okay. So it can be transferred in the orbital way, it can start carrying up the electrons or carriers, or it can be actually transferred by some in orbit and so on, couplings and the molecules. Inverse Faraday effect does not require to have topological band structure, it doesn't require to have a method. In fact, inverse Faraday effect was first proposed in 1960 for plasma. It works at the level of a single molecule. And then the other thing of this thing is that this guy didn't even bother to put the original paper and see who wrote this. So we did a group of Kimmel and whoever, Pertel and Kimmel, you look at others, they made very important observations in this field. So one example of the role of this inverse Faraday effect, I'll just highlight here is the 2007 paper when they proposed to have magnetic memory. So you have a ferromagnet with a main polarization up and down here, and you send a circular polarized light, sigma plus and sigma minus, and you're drilling the holes where you're flipping magnetization of this magnet. See, I kind of this droplets about 9. So it has an ability to flip spins or flip the magnetization. All right. I don't remember. It could be anything, it doesn't require any symmetry. So the point of this nonlinear effect, thanks for the asking, you have a non-divergent symmetry, no fake inversion symmetry breaking sample. Population, have a molecule. Yes, magnetization, and it's because you go and beyond the linear response. So all your linear response characterization fails because the field of light itself produces enough of polarization, produces enough of the sort of like steering. So the idea would be that technically, if you think about this, what is stability? Stability is efficient that lets your observed current to gauge potential. But if you have already in this kernel something which is basically already steered up by the current, so you look at the effect more K due to A squared, then also all the bets on the symmetries are off because it's light itself already seen. But I don't remember per se what the sample was. Right, so coming back to this idea, there is a lot of this linear reduction effects. For instance, you can look at the Floquet stack, you take a band structure and you replicate it, but in Floquet, which is a set of repeat units. So also the Nordita experiment on the surface states topology, requires pulse. So as long as the pulse is eliminating the sample, you see the stack of these Floquet Dirac cones, and it's very interesting work, very exciting by them. But I would say that this case is a sort of linear effect in the sense that we just have the ladder of the Floquet kind. So this example of another linear induction way, it's dynamic induction of superconductivity in the potassium 360, where they show that typically potassium 360 conductor is a TC of about 30 Kelvin, maybe 36. But they actually do this pulse probe experiment where they measure the transient conductivity, and then they show that in the after they eliminated pulse, they measure the optical conductivity and they show that this is absolutely something get absorbed and really presumably some transient delta function. There is a lot of philosophical debate whether it's superconductivity or not, but at least the idea is that you have a recipient and it's possibly superconducting character relations. And so that would be at least a goal. Right, so I'm saying that at this point we have this particular example where the early on Cavalieri group was one of the pioneers of this technique. They were arguing that this is a superconducting state, transient superconductivity. Lately, I've been talking to him, and he has some other published results, or maybe soon to be published results about the Meissner effect. Same setup. So it might be not superconducting state, but they do have a Meissner effect as well, elevated in the temperature. Right, so I was just saying, by the way, that whatever the framework we carry on from the equilibrium to non-equilibrium, it doesn't have to follow. Might be that we'll have to adjust a little in the language. Discussion. So basically, it comes from 0 to the good fraction of. So he sees the basically induced magnetic state. A diamagnetic and the rectification sign. And I think actually there is a preprint. He was telling me that this is even going to be published soon. But yeah, by talking to Andrea, he said actually, people get him quite a bit about whether it's superconductivity or not. He said, call it whatever. This is phase with elevated Meissner response and response. But Meissner was perfect diamagnetic, large diamagnetic response. So there is an extra piece of the work coming in this field. All right, now I already mentioned Faraday effect, so inverse Faraday effect. Let's just do the examples of the. So example, you know the story in the movie, the wheel doesn't spin. So story is that what you have actually say you move the thread, you want to move it the second, you have a thread on the wheel, car or bike, whatever you have, and then you have a camera rate, shutter rate. And by the way, our own eyes are also have a certain rate of process. And so when these two frequencies match, it comes out is a total like a DC point where things as good the thing appear to you to all observational purposes, not moving. So I just want to run the movie. And pay attention to the thread. Here it is. Come back. So this is my experiment. I borrowed the bike from my colleague, just basically. Patrick was holding the bike, we took the video clearly. So I think actually for all purposes, it does highlight the direction of what you're going. Take two harmonic processes, if you fuse them together, and actually at the end of it, you get something in DC channel. Okay. Is it thermodynamic? I don't know. This is like an equilibrium. Call it what it is, but basically for observational purposes, your signal and something like video would measure in the tunneling would have no AC component. Okay, so like I said, example of this thing, trivial example of diode. Diode is a standard textbook rectifier. And notice actually the diode itself is a linear in a sense, you don't do anything, but diode is like the media already have no linear stability because diode has a very nonlinear characteristic. I versus V. Alternatively, you can take a linear media, but basically also for diode, what's happening is very sinusoidal input voltage, for instance, and output will become an output from heaven. You see component. And so notice I start basically steering your thinking towards quantum states. I put the cats here, so I have it sending something in, something comes out. And so, but basically this nonlinear stability might actually lead to the output, in DC channel. Where I want to spend time is talking about input in and input out, input 1 and 2, producing output, and get DC signature. And you can, once you start wearing this rectification glasses, it's fascinating. All the standard, a lot of the standard technical examples of physics I know can be rehashed in this way, all the way to very simple elementary quantum mechanics. But let me just show you this thing, Poynting vector. Obviously, we know that light impinging on the plate produces pressure, but light is made from the oscillating waves. How come you have a DC pressure if you have oscillating waves? Well, it's because basically the Poynting vector that measures the amount of the energy momentum carried by the photon is quadratic. So you do the math, EMP oscillates with omega t, and then in phase you have a DC part, which is actually one here, and you have a twice the frequency. As the DC part that rectifies, it gives you net pressure, pushes. And this is played by light. So, put it differently, there is a lot of conversation in the physics and the optics about the second harmonic generation. We have some crystal which has nonlinear stability, where you send these two frequencies and two beams of light, and you have a twice the frequency. But the flip side of this has to be that there is a harmonic part. And whether you choose to look at DC or not, it's up to you, but it's there. And so that's what I will just say, that very often when people talk about second harmonic generation, there is something happening in the steady channel. Now, then I'm making this very quickly, this thing. So if it's true for classical light, it should be true for quantum light. If it's true for quantum light, it should be true for any quantum field. So I start putting A's and B's in hats, and I don't know exactly what it means, right? But basically, it kind of means that you have an operators, and so let's pull back for a second. Look at the conformal field. You can have a crazy fusion rules, and we already like do some about the fusion rules or the operators in the field here describing molecular statistics, like the conformal field theory. We know that actually you can use this field A and B and produce the fields. But quantum mechanics is totally possible. Take two apples, merge them together, and get the orange out. This is actually like one of the beauties of quantum mechanics. Now, if it's true in static, here's another big thought. If it's true in static, it should be true in dynamics. Why? Because the static and dynamic has to merge some. And it could be subtle, there could be some differences, but technically if it's true for the static inputs, it has to be true for the dynamics. And so then, if this is true, for instance, look at this as a addition rules for the angular momentum operators. The angular momentum L1, angular momentum L2, then I'll have here outcomes ranging all the way from L1 minus L2 all the way to the highest rank. So if this is true in the static, then it should be true in the dynamics. So if there have two frequencies, omega 1 and omega coming in, that all these fields, used fields are coming in, they probably will have, not like, they will likely have the harmonic content was in some different. Okay. So that's what I mean by the or at least I'd like to develop the framework to understand. That's what I'd like to understand better, how I can drive dynamic order. Way beyond this harmonic generation, way beyond the light. And the goal of my talk right now to show you how I can do it in some other fields, which are unexpected. Okay, so I will show you some examples.
We did explain that. Okay, just to recap, inverse Faraday effect. You have this, you have this, you have a DC magnetization. Here are the heuristics of it.
For orbital effect, the effect of the photon coming in and sort of talk about the kinetic equation for the metal. Talk about basically one electron in the whole universe and basically subject to incoming superconductivity. So you have equation of motion where the electron, the bound state of the electron to the ion is not moving, and actually you start steering, so the electric field is actually circular, right? You start steering the electron around. Transferring the angular momentum from light to the electron, literally like what we have in coffee or steering it up. And so angular momentum of the light with the proportions of the electron with the proportional R cross R dot. And then you work out whether you want to look at the spin dynamics or over damped dynamics, which technically R is proportional to E. So this thing goes down to something of star. And the structure of this equation is such that it only works when you have a surface polarization. Vanishes any linear polarized. Okay, so the diagram I'm looking at is actually I have a 2E's coming in and I'm having rectified this. That guys off as a function of frequency. Like I said, it's been seen already on the molecules. For the molecules, typically it has spacing and the light about this frequency of common orbitals. And so then this low frequency divergence is never an issue. And some of this is basically in the disordered metal, this one over omega should be played by some damping or K rate or lifetime terms. And the other piece is that actually technically the way this equation was derived is assuming that the light gauge potential proportion E divided by omega. So you have to take care of this when you see you will not have a diversion gauge potential. Yes, I'm anticipating that maybe there is some pure conversation. Actually, the limiting of this expression is an intrinsic conversation. No problem, I agree. And like I said, the first to observe this thing, it's somewhat unfortunate name, but the first to claim this was Kitaevsky, who in 1960 was working on the plasma physics. I've been told that Kitaevsky before he turned into this old atoms, but quite a few actual works. That's another interesting question. Why in the 1960s we were working with plasma? That's a conversation.
Where do you get the 1 over
Omega squared. R is E. Just have R, so it's like 1 over omega squared. R dot is 1 over omega. But you can do the full kind of distorted theory propagated. Any other questions? Yes.
How big would this effect be, like in terms of real numbers?
Well, that's something we're looking at in a variety of setups, basically for the orbital effects. Technically, we find out the effect is as big as one Bohr magnet per atom.
Why does the absorption of protons carrying magnetic distance rise? Now,
I don't know. It's a first of all, check is non-resonant. Don't have non-resonant.
one is it's the effect of the kind of Raman type of thing, where you take a photon get absorbed, but it's something because it's still not counting when the electron is if no photon gets stuck. But it's a good question. I should have a better explanation. Any other questions? Yes.
About the fusion. So there's some sense in which to talk about the fields measure. Like if I think about the gold, the picture of gold, that delta function emerges. Initially get scattering into the state, including those that by the energy.
Yes.
And then eventually. How does that work with the fusion? I think of them as being
don't know. I didn't put the rules for the conformal fields in time. I'm just vision. Technically, what you're saying is exactly correct. Given that there is an internal dynamic of the system, magic is not one-to-one. Pure harmonic compensation. Steady state, yes, but in the brains, like you have a whole profile, so the full delay function. Stefan Blögel revisited this list later on, pointing out that there is more to this than just harmonic. Thank you. So, but nevertheless, I stand by the claim that dynamically there will be something induced. It might be that actually there's more to this than just omega 1 plus 2, but technically, if you have it steady, this kind of happen for the dynamic, regardless of what the protocol of driving is. Okay, now, so let me show you something about this. So, when they start talking, people say, yeah, but this is standard light, especially if you talk to optics guys. They say, we know this is all plastic. I'll show you a couple of examples, and at the end time permitting, I'll show you something we're doing with the quantum paraelectric. Okay. So axial magnetoelectric effect, this is what I call the fifth part. So obviously, that there is this derived in wild materials. I think the ideas of these materials that they have an unusual electronic property, something that looks like a thermal surface gets replaced by the Dirac column, depending what can have as little as nothing for the temperature. You have a whole set of phenomenology about or microscopics about surface states, anomalies. What's interesting is that you have also this immersion gauge field coming from the fact that if I do twist the sample, these carriers that know about these nodal points, just something for we used to know at least the context of helium-3. So we wrote a book about universe in a droplet of helium-3. It's kind of true in the sense that in the helium-3 it's been known for a long time that the texture of this orbital vector L contains all sorts of gauge fields. And so it's very interesting how it finds its way now in this condensed matter setup wild systems. I would point out that since this particular feature, presence of the topological band structures, is a feature of single particle problem. It holds up also for the world. Don't even need to have the same term. Okay, and so when these Dirac materials or wild materials, what you see is that you have two Dirac cones, and the position of this or a number of Dirac cones, and the position of Dirac point go by something called vector B. Now, if you do this in the 3+1, you can have all this chiral matrices, and there's this phi gamma 5 matrix. So it is known that actually strain and other independent effects on this E field, it measures how far away we have from points, nodal points, happen either in at non-zero momentum or they can be shifted in energy. And so these B fields are typically what's called axial. And for instance, the time dependence of this B field would be look like a axial electric field, and also gradient would be zero. Mu runs here from 1 to 3, 4, so zero component would be. And the special gradients of this thing look like
magnetic field. Now, the properties of these fields, E5 and B5, is different from conventional electrical magnetic field. So if you do this full analysis of the current expressions for the standard U1 current and for the parallel current, we'll find out that, for instance, this current is a charge even, whereas the other one standard magnetic current and also I should say that parallel anomaly and some transport and environment physics happen. So what's important for me is that actually you have E5 and B5 and look at the selected field 5 is even on time and inversion. And the magnetic field B is a lot under both. So it's totally different from what the usual intuition of. Okay, but nevertheless, there are the synthetic gases. Okay. So next we make the following observation and write down this expansion magnetization as a function of the magnetic field, the same in type. What I'd like to pay attention to is this term here, which basically couples the two electric fields. Remember this E. Oh yeah. Oh. Need to do something. Have my own power source. I thought this one is a Is it out here again?
Right.
Oh yeah. We'll take it. Famous last words. Is it better? All right, maybe. All right, so notice that E is how would you say E is even under everything. Magnetization should be on. So unless I have something actually done to the media, unless I have this tensor, there's not gamma 5 net. I do something in the media, break time reversal. There will be no induction magnetization. And in the light, technically, I do impinge it with the photons that carry angular momentum, so it should be okay. Plug in this. Me? Yeah, that's wrong. Yeah.
So you said Chinese photo. So what is superpolarized? Something superpolarized?
Not yet. Not yet. Very important. E5.
Can you separately polarize it also, or?
Okay. I'm sure. I'll show you. Yeah, there is no light. Okay. Any other? So I already said the strain produces the gauge fields. Time dependent strain produces gauge fields in the field. So just to highlight something that seemed to be, to my surprise, is forgotten, but back in the early days of the Dirac or graphene story, Harry Manoffer built up this. It's like a baby step of what talking about using this cubical plasma of the crystal. One by one assembly of the crystal. Right, where he built up artificial graphene, which is basically tunneling. You can see sort of like a Dirac cone merging, and this is simple atoms on the surface of the top. Now, what he did later on, or in the same paper technically, but he stretches graphene. So stretching of graphene in a particular fashion produces the stretch texture is designed specifically to maximize the gauge field, the synthetic gauge. And what you see here is actually you're showing that you can have this lambda levels. A published version of the paper, actually, field going all about 600 So this is actually static structure, but deliberately stretched. The next thing actually for your question is going to be, I take the structure, I go oscillation between here and that. I will do it by sound. Proposal is actually to produce gauge field.
Now, for that, I basically the great help. In fact, there's something we should shape the thing here that duration that you can do time dependent motion nodes in the Dirac and Weil. So this case is something that Telluride, where they show that typically it's a non-Dirac and Weil state, and then they send a very large intense terahertz light. And the light basically shakes the sample film. Because of the shaking over the symmetry or something. And basically you have this emergence. Yeah, it's crazy that either wild points coalesce and actually can merge together in sphere and become real metal, or they exist. I don't know what's going on.
American is fine.
Should be working.
Power 4.5 to everything.
I was totally confused.
Use it.
Yeah, it's me, another screen problem.
Okay. Can't you tell if it's charging? Tell if it's charging.
Yeah,
Is it?
no.
What did you try this?
Is it charging?
Let's see. No.
No? Is it this thing? Can you speak?
Maybe.
Yeah.
Maybe I'll.
Ready? This side?
No. No, no.
Charging? No?
So I would say this.
Can we check?
Wait. Battery status.
Remaining battery saver on.
So not charging. The same?
Let's check if this is supplying power.
Yes.
So we know.
Where is the?
Yeah.
Okay, this is not supplying power here. Yeah, I think these ones aren't working.
Yours are not working.
I just spoke last year as well. But that one. So what about the one here? Those are more. These ones.
The laptop. As in here.
All right.
Now?
Okay.
Yes.
There's 11 minutes remaining, so
Not charging?
no, maybe it's me. Maybe I should read.
Damn, try the other side. Is
No, no. Worked yesterday.
Right now.
Yeah, guys, it's, no, now it's working.
it's working?
Yeah, okay. Cool.
Yay.
What is it?
Yeah, I noticed the switches too. Yeah. Right, okay, so online we're coming back. All right.
I did. That's.
Oh, yeah.
Yeah. It's not shared now, I see. Oh, you have to do something. Yeah, there's a lot of movement here.
There you go. Yes, me.
And two. Well, anyway, so what I want to say here is that you can manipulate nodes in two ways. That is called basically the idea would be to put together crystal and together with the phase file. Technically, it would work if you have a square lattice with square surface with natural degeneracy and proximity of the frequency form. Yeah, that would be the proposal, and I'm trying to get to the equations. Here they. Okay, so clear that there is no photon, but it's now transduction of angular momentum of the photon. What is it? The answer is that because the gauge field now, E phi itself, remember the gauge potential is gradient. The active field is another gradient. Let's talk about it this form. What's happening is that actually, if you have two electric fields, you have a factor of say 4 Qs in front is 1 3 Qs in the denominator. Technically, magnetization now will actually rise linearly with frequency. Which some physical dynamically. This is a calculation, it's not a sketch or particular, in this case, roof and the W Martian trials in metal. And we took his leading edge of the frequency of about gigahertz, huge displacements, large intensity. In fact, the scale on E squared becoming intensity, right? Better the more fluency you have in certain frequency, squared. Right now, so this was an example where I try to address the concern of some colleagues of mine saying this is what you're saying. The example of this, taking the idea, applying, transferring one set of degrees of freedom to another, which is not exactly second harmonic generation repeat. All right, so technically what I have is that you can file away that we do have the same DC induction. We should write a Wikipedia page. Or deviation. So it's in this paper, in fact, it's tiny, technically observable, but it's going to be pretty complicated. It's more like a matter of principle exercise that you have this idea of the twin coming fields don't have to be photon. Again. Now, what I want to do next, given the time we spent let me talk about the inverse Faraday effect in quantum parallel.
Building up on that, in fact, sort of like project was going on in parallel. Let me show you something on the extending this to parallel. So the hypothesis is that if I have the parallel, is the second parallel, quantum parallel. So I should point out, by the way, the fact is that even though E field itself is a pure expectation value, because already can have a net DC net. Technically, this thing is actually working out in fluctuation. I forgot to mention the simplest example of rectifier. In some dimensions, performance, hit them up, performance are totally random. But if you have no linearity in the phonon, which is of course, you have no linearity, which means phonon-phonon interaction. You have no linearity with potential, you have x squared, you have x fourth, one times x fourth, you have a fourth order phonon-phonon interaction. You basically, you have to have a cubic. What happens is actually the phones rectify and your solid expand. You have a DC expansion, solid, even though it's randomly flying around form. That's what happens in the example.
Sorry, Sasha. This
Yeah.
has been observed, yes. What you just said has been observed.
Thermal expansion, sorry. I mean, the fifth effect. Fifth effect.
Yes.
No. Because yeah, so technically, I have an experimental verification of the idea, which is thermal expansion. Right, so the idea then is, I take a P field, and then imagine I have a quantum fluctuator, which is of course for me would be SEO from titanium oxide. And then what I will produce is the properties theory now. So my input fields are going to be right, and the output will work. And the idea basically is extension of this dynamic fluctuation of periodicity producing again sort of previous moving charges producing properly moving charges producing. So the setup here is a strontium titanium oxide in crystal. The big spheres are strontium. Inside we have octahedra of titanium sitting in the middle, and we have oxygen. So titanium sitting on the scale, and most of asymptotic point responsible for ferroelectric order. This is so transverse of Q, titanium moves right, and this morphing mode, vacuum mode because titanium charge located to oxygen. So there is a balance between the charges of titanium and oxygen. And for this STO is a quantum paraelectric in the set that below 30 Kelvin. All predictions will give that it should become ferroelectric, but their vision is still wrong. Works. Okay. So in the case of quantum paraelectric, which is STO, this thing happens already without any effort. You take it out of the furnace, prepare samples, already formed. Don't need to do any operation. Take, for instance, European titanium oxide, the profile of the potential is so much deeper that the pulling crystal parallel. So this quantumness comes from a very shallow level well. And group of Gil-Londrich and people around him spent quite a bit of time hammering down this point that STO hasn't grown up in the case of ferroelectric, which is a paraelectric. And they have this whole diagram where they talk about potassium compounds, different variants of the STO ions, where we can move this away from this standard quantum critical funnel, but STO itself remarkably. It's one of the oldest, I should say, one of the oldest sources. Discovered in 1960. Also is remarkably very interesting. So the idea, therefore, is you send light, it's just the light with light ions, couples with the light, so the phonon have to come and tap into the phonon steer. Maybe more. No problem. I'm going to show you now experimental results. Martino Bassini, basically are the main drivers in this group of fundamental. The idea then I have a two degenerate number from temperature, say below some 110 condition. The next cubic, you have two degenerate form omega 1 0 and 0 1. I'm going to cancel that axis and I will start steering up form. Still start steering up to light, but basically light is just a means of steering up. Light is not going to be. Technically, the game will happen on the steering ion motion. So what I feed in is a frequency of about 3 terahertz, which is essentially resonant, even though I said initially it's not resonant, but 8 bound out the effect. You coming with the light of this gray peak here in the middle at about 3 terahertz, and you read off polarization produced by the sample. Wait time at 6 of okay, so the algebra, of course, is here you have some of the future text to the proportion of the second order and every single black light. Here is the trace. This initial, the orange one is the right circular chloride light shown on the sample, and the gray one is the circular chloride light. And what you can see with the time delay of a few picoseconds, start seeing ringing magnetization. How do you measure magnetization? You measure from the same Faraday effect. So what you do is actually you do sort of pulse pump probe experiment. You do this first. Terahertz light to the circular polarization. First, because polarization is now for probe. And then they showed also that the effect of the field fine. I showed you the same online algebra. The effect comes out to be much larger than here. Fact is exactly something that comes out to be one more magnet. So there is a question about what's going on, and then we do have some suggestions about this in the interest of time on one, but feel free to ask me at the end. There is a surprise in a very simple critical kind of discussion we have. Exactly. We had a question.
I was just wondering, so it's ringing because what? What is the ringing due to?
So look for a transform of this. Here comes flow ones. This is your 0.3 terahertz or 0.6 terahertz. And this fast one is the sum of the frequencies of the form. So I should do it. Now, how do you know it's not inverse for the effect from the light? We know it because A is a delay, but second characteristic times C. So I'm not sure we're doing time wise. Basically I can stop here. I can
Well, you started around an hour ago.
that narrows it down.
It's now 5 minutes to 1, so you still have 1 more minute.
I can do, or I can stop here, but I can show you something a little bit more elaborate on this analysis of one point under the stage cake.
Just maybe like questions.
We can do either way. So maybe here's a suggestion or allowance. Let me quickly run through the idea of modifying one critical point is like the fast shaping block. Okay. So with respect, unless somebody has a pressing question now, yes. That would be.
Just one question. So, but this isn't, you don't need to do this in resonance. You can do any.
Yeah.
Should
You
still
don't have-
see.
exactly. It's not resonant, but technically, obviously, the transaction for the photon into phonon is best when you're on the phonon resonant.
I can't quite. Oh. in recent have some higher component.
These are the current forms we're steering up.
What dynamic?
Yeah, beautiful. Thank you. So building on what you questioned me, remember I showed you the STO as quantum parallel. So imagine you park your STO and you see the quantum principle. You measure magnetic system. So we did the analysis on the magnetic susceptibility because of the fluctuation. Because you have E, two of E's. You have a ferroelectric vector, can have longitudinal fluctuation, and have a transverse fluctuation. Transverse fluctuation, for example, they go down, bad, but they get bigger and bigger in terms of the volume. So we get like slow moving chunks together. Because of that, through this expression, we can calculate magnetic susceptibility. And at the very least, it's large. And there is a theory which is basically the so what I'm saying actually is the vicinity of paraelectric and ferroelectric condition where you have soft modes, ferroelectric degrees of freedom. Once you look at the magnetism. I didn't bring up this paper, but there is analysis. Technically, we get the divergence. Not because of the drive, but because of the same performance, so taking advantage of the quantum fluctuation.
This would be harder to engineer, but could you in principle get something additional in let the plane of assessment?
Plane of sample?
The plane of the stir. So if I could change the axis around which I would take.
I haven't thought about this. I'll tell you what I thought about, which is actually going for the Gaussian fields which have an angular momentum. So for this expression, there is no change. But presumably there are some quantum numbers, there are some quantum states, Gaussian linear beam. Beam is with the phase which has a high angular momentum. Also, it's kind of related to what you say. I have some dynamic and the incident plane. But so, your question, I don't know exactly. Maybe I'm mishearing what you've been asking. It's not clear to me that there will be effect.
No.
Okay, so now, am I allowed to do this a few minutes more or not? Huh? Okay, cool. All right, so basically, computer stabilization and rectification of quantum order. So basically, you have a quantum critical point. So far, I was just doing the simple response, taking advantage of the quantum critical fluctuations, and showing you how we can steer the formats. So let's do a little bit more than this. Let's have interactive theory. So this is Kapitsa pendulum. Kapitsa found out like in about 53 or so. Take a standard mechanical oscillator, turn the pendulum upside, stabilize, you shake the base and go. The shaking frequency of the base should be much higher than the frequency of the eigenfrequency. Right? So the effect is that what was happening technically, I'll show you here. So you write down the equation because an oscillator with here, if you write down the equations of the damped oscillator in the presence of the motion of the base, it basically modifies drive term. So it's modified phi is the base, and actually this theta is the angle. Phi is the shaking angle, and theta is the angle. And the key point here is that it's a nonlinear effect that comes as a result of this going fast and slow degrees of freedom coming into potential that controls the motion of the oscillator. Right? So what is happening is that you write down the standard like a cosine profile out here first, phi, start developing this metastable medium. And like I said, it comes as a result, technically what happens in the flow and positive. Because you cosine phi potential has basically now add two phases, fast and flow, you expand it, you write separate equation motion for fast and flow. They couple. But to second order, you can integrate out the 5 degrees of freedom, and that produces a nonlinear correction potential. So for those of you who are like a trained, conditioned can be the Fourier conversion. This unfortunately is beyond Fourier because I didn't take interaction. Cannot Fourier recognize, but it's likely to be very. Whether it's Fourier or not, you can talk about the high frequency harness expansion of your Fourier stack, or you can do that first order interaction. So the idea is that you have this set of states, you basically go to this higher frequency coming back, and this through nonlinear stability is modified while in the state. Okay, so it's been now coming up as another interesting example of controlling the quantum materials. People talk about export. There's a repulsive BECs and people talk about the capacity. And all the way up to more recently, so these ideas of using capacitor oscillator analogy for the Josephson junction property. I have driven organization in the Josephson junction couple AC Josephson. So I already mentioned that the STO is a quantum paraelectric, so we're going to be seeing here. We have a theory. We have some approach to calculate this. We use a nonlinear potential for the constituent parallels of the STO. We have a quadratic and Polish term. And it's important to have this beta 2 term, which actually has this cross of why. Because running ahead, I can tell you if you need to keep shaking electric field along this X polarization, only have a X polarization. And effectively that. So polarization develops direction vector even. So then so what indeed is happening is that you have a set of minimum profiles basically in the given lambda when the mass term is positive, sitting in 0. The case of minimum is alpha is negative mass term, and there is depending on the relative strengths of beta 1 and beta 2 term, you can develop 1 0 or 0 1 or 1 1. In this case, even though S0 will be. Then we said we have an impinging light, so we technically mount the driving term. The beauty of this paraelectric vector couples linearly. For instance, if I were to look at the superconducting order, like I cannot couple psi, size here, linear. You work out the corrections of this term stability by degrading on the spot degrees of linear. It's important. When I should do something. Then what happens is that depending on the beta 2 versus beta 1 profile, we can stabilize either 1 1 direction, 1 0 direction. And the beauty of this is that remember I was showing you the angle phi. So the light can be actually polarized, that incident light can be polarized with the angle phi, the main axis of the crystal. So the effect is that even though, for instance, I can have 1 1 polarization stable, that is all rotate. So basically, control would be for this experiment would be fairly easy to rotate either polarization. Easiest would be rotated polarization, like and the physics of this is very similar to what I was showing you in this metastable profile of the oscillator. Depending how you drive, getting so for instance, take this red curve here, and they say you have a minimum at 0, and you drive along this 1 0 polarization, then you develop along 0 1. Well, this metastable. Right, so you're rolling down from this. Again, polarization developed always is that requires this would be an analog of this Duchy oscillators. There. Now, since I promised you very clearly to tell about one critical point, so what's on the axis here? So here's the outcome of this calculation. Vertical axis is polarization, my observed order parameter. In the plane, this axis is alpha mass term, and into the plane is my electric field drive. transient magnetic. Remember, the effect is actually non-resonant, so frequency is not particularly important. So for negative master, you already have a ferroelectric phase, but for positive master, technically you have another parameter P with red dots are zero. Aside from this here. But then as I increase my magnetic field, electric field, then this thing takes off. Find that phrase once it where the formerly electric phase. And the effect of the signal power will depend on the conductance tenses power of one. So it's finite, it's like a bicycle in Lambda theory for the measure of conductance, not exactly standard physics. Let me just now what we want to do next. Well, I guess I think we finished. Now the question is what to do next. Filling out the catalog possibility of inducing unusual quantum numbers. Right, like what is the idea is dealing with the quantum system, becoming some object that can be quantum number. Some of them get transferred to the quantum material or material world. You can induce unusual order in the material, even though nominally they are not there. So just to finish this, next step for us would be, for instance, to look at the effect of the incident circuit polarized light angle. Remember my analogy of steering up electrons from the spool? So I have a non-magnetic field applied. I have a set of speaking that I got shine the light. And basically suddenly electrons flow. Something that has to be on that. Cannot move with damage. So they have the phase. So when you detect that, they should be have right in the so Priya been working on this slowly, daily. We have now results for the metal. You take niobium, you apply basically available to reverse field. You can generate magnetic moment system field exceeding HC1 niobium. For the amp, we'll start. We have a field larger than the penetration field. This answer holds for Balatsky, pulling it down to voltage. Possibly making calculations. That is here, and then we estimating 1,000 to the core magnet per unit cell. Not big. So the idea then is spirit of this one station. What is it? One being squadron and another one. Your power right body system, power to the raising. Very interesting, but turns out that technically this is very complicated. Feeling one can be used. So there's like every time you think you know that's not way. So that's why we had an attempt at the claim on this attacking calculation. Okay. All right, thank you for your attention.
So this is an experimental question. So do you need to use pulse slice, or can you have continuous light?
Calculation is CW.
Yeah, so you
Yeah.
can do this with continuous light. What about heating and stuff?
Getting always is bad.
Problem.
Heating is bad.
Okay, but this experiment you're talking about was done with.
Yeah, no, this was false.
This experiment was.
Priya, the theorist right there. So she's working with me. We are not experimentalists. We propose it. But you're talking about STO. Superconductivity has not been done. Nobody looked at the inverse Faraday effect in superconductor. And the reason for that, actually, it means you have to have a, if it's CW, you have to have waveguide or something. Always like Kelvin volts. So it requires basically multi-mode. Running, like probably could be done with some coils.
Also, sorry, just one
Yeah.
quick question. When you shine light, do you expect to generate multiple vortices inside this?
We don't know anything about this, like you're saying. What are your way of answering? I don't know anything on this. We start looking, but technically what's happening inside of the beam is micron. There will be few, but it also depends on how much vorticity you transfer. It's conceivable that it can have one. I will take like 100, I will take 1,000. Let me just see what's going on.
You have to create vortex.
Yes, right.
Like you have it into.
Yeah, exactly. Yeah. So at the edge of this, the thing that have probably like a massive amount of compensating antivortism, swirl over the sun at the edge of this beam.
Anyhow.
Yes.
So I think I'm happy for daily life.
Yeah.
Let me say
Yes.
and related to the question of heating, so get some points. Well, this is sort of mapping this back in. Right?
So first of all, hitting goal. And so I don't have any plans. For me, hitting is a normal death of the internet. Yeah. But I think it's really like people find it that it's go to heating goal. Do something on this. They're not relying on any of this. So if you believe that there is a induced magnetic or spirit like amplifications of the source. So the right answer to the question would be you have full dynamic theory. Yes, basically with the bus. Yeah, but then they gave a rundown. Well, they 5 and 4.
There is not a.
No, there is a zero dynamic, but there is no feedback attack. There is a dynamics of the so initial stability. There is a dynamics of the initial stability of the fund. In fact, how we find the stability, we actually take initial stability, find the force which I can augment with the previous. And we write out and see, and I look at this zeros or poles of this. The dynamics at the roll level, first step of the path forward, can put it on critical indices. So consistently calculated. Over the answers to some questions.
Bearing in mind.
Yes.
Right. That is. And
I'm the one standing between you and lunch.
Also in the spirit of this conversation, really not. But in some sense, what you're doing with it's adding terms that weren't in the non-trivial Landau theory. Is there any possibility of doing something for it? So for example, like soften a channel that was previously on every change the number of songs.
I think yes. I think actually at least it's possible to have some polarifonic training where whatever incoming quanta can get mixed with the incipient quantum degrees forming their own proper.
So just like what I was saying, think about cavity. So, I guess you're putting the cavity, light fluctuation. Presumably photons will get entangled with heat. Yes. That's another piece. I would say yes, but I think we have maybe there is a way. Yeah, I should.
So, yeah. Still needed this.
0.3 Kelvin.
Yeah, I agree.
So definitely, I think it should be bottom line for all of this. We found out somebody in Michigan has this dual probe with Carolina in this area. But whether or not he has access to this.
We have both, but we don't have. We have light and STM.
And you can have a circular chloride light.
Yes.
And Sasha. We're starting date again. I propose we meet at 20. At 22 the hour, 20.
Within some time.
Yeah, so it's supposed to be after 14:40 is what I suggested. 10 hours, 10 minutes later. Just enough time to get. Yeah.
Like, I think. Here in this charger, he's the charger.
Yeah,
My master.
Sasha, I'm gonna get my.
Yeah. You're back.
Yeah.
Charge a little bit, thanks.
And I should.
Okay, it's not.